These are the notes for Unit 4, Day 1, and they start on page 3 of your packets. And today's notes are interpreting the meaning of the derivative in context. So basically what that means is we're looking at, I would just call them word problems, right? Contextual problems. And we have to know how to decode it so that we can use the appropriate calculus. So the essential question then is, how will I decode calculus problems? So that we can make that happen. Okay, so let's just kind of talk about an overview of what decoding means. So, we're going to employ some average strategies here. We're going to read the problem statement, underline some pertinent information and key vocabulary so that we can kind of create a roadmap here for what sort of solution we need to do to this problem, for this problem. So let's talk about some vocabulary here. And two vocabulary terms that we keep coming back to are average rate of change and instantaneous rate of change. So we know the average rate of change means algebra slope, right? It's an average, it's 2 points, it's the secant line. We don't have any calculus involved here. This is just going right back to algebra. So when you see average rate of change, or I call it average ROC, think algebra slope. That's what this is. Rise over run. Excuse me. Okay, instantaneous rate of change. Instantaneous rate of change is where the calculus comes in. So the instantaneous rate of change is the derivative of the function. So it's f prime of x, or it's dy dx, or it's the derivative. Those three all mean the same thing. Okay, and this caveat here, provided the limit exists, we know that the derivative comes from using the limit method. So that's just kind of a completing statement in the definition of instantaneous rate of change. A lot of times they have you approximate the instantaneous range. And if they have you approximate it, then we are right back here at average rate of change. We're right back here at algebra slope. So remember that approximation, anything that asks you to approximate something is taking you right back to algebra. Okay, so let's talk a little about decoding the context. Can I use a calculator? So that's the first thing you should be looking for when you look at problems. Is this a calculator problem? If it is, get the calculator out right away. If it's not, then you shouldn't be using a calculator. Do I need algebra slope, or do I need to differentiate? Do I need to consider simultaneous events? So two things happening at the same time. Is it asking for marginal cost? This is really a specific decoding situation, but marginal cost is the same as instantaneous cost. So if it's asking for marginal cost, you know that you're taking derivatives. Just like if it's asking for average rate of change, you're doing algebra. So when you see the vocabulary marginal cost, it's calculus, it's instantaneous. Let's talk about understanding the answer. So is the derivative positive? If f of prime is positive, right, if that's the derivative that's positive, then the function itself is increasing. Think about a positive tangent line, right? It slopes upward, which means the function values are increasing or moving upward. Then the opposite of that is the derivative negative. If so, the function itself is decreasing. And of course, the last scenario would be, is the derivative 0, right? And so is the derivative 0 means that the function is switching from increasing to decreasing, or decreasing to increasing. So increasing to decreasing would be like, going over the top of a hill, right? Or decreasing to increasing would be going through the bottom part of a valley. So we know that those hills and valleys have tangent lines that are horizontal, which means they have 0 slope, which means they have zero derivative value. How about the understanding the units now? So decoding calculus problems, working with contextual problems, usually means we have some sort of units involved. So we need to understand that the units, when we're talking about derivative, the units are ratios, right? We can see that in the Leibniz notation here. dy dx is like a ratio, you know. So that it kind of reinforces that the derivative is some sort of instantaneous slope. The d's are basically stand for differential, but they're really for like change in y and change in x, or like little deltas. So the units are ratios. So some examples like meters per second, if we had a question that whose context was motion, or minutes per inch. So you know, this would be like how long it takes something to move an inch. So notice the unit of time sometimes is in the numerator and sometimes it's in the denominator, depending upon the context of the problem. We get cubic yards per year, you know, if we're talking about, you know, the yield of a crop or something like that, or degrees Fahrenheit per year. So if we're talking about maybe like global warming or something like that. Or we could even change this up to be like degrees Fahrenheit per acre of farmland processed, because we know that that contributes to a global warming situation as well. So each time you differentiate, you add another per. So for instance, if I take the first derivative, I would just have a single per. So like meters per second. If I differentiate it again, it would be meters per second, right? So I'm choosing this unit because you're familiar with the units of motion. So if we started with position, which would be in meters, then we differentiate, we get velocity, meters per second, and then we differentiate again, we get acceleration, meters per second. We'll talk more about that in I think the next set of notes. But so that's why I have this little note down here. It says each time you differentiate, you add another per, add another fraction bar, so to speak. Okay, so justifications. When it's asking you to justify or explain or interpret the results, what they're asking you to do is reference the derivative by name. So make sure in your justification you're saying f prime of x is blah, 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 or the units are specifically this, and reference everything by name. Don't use you know, words like it or this or something like that. Reference the function by name. And use the correct units. So I kind of alluded to that just a second ago, that when you interpret things, you want to be sure we're using the correct units. Okay, and I just saw this pop up over here. I must have the timing wrong in my file. So this is the calculator symbol. We've seen it a lot on topic questions and stuff like that. So when you see that symbol, you know it's okay to use a calculator. Or if you're on a calculator part of an exam or something like that, obviously it's okay to use a calculator. Okay, so here's a little kind of a diagram for the problem solving process, right? Typically we start with a function. And so our first crossroads are, if we're given a function, we could be given this function in several different forms. We could be given a table, we could be given a graph, or we could be given an algebraic expression like f of x equals. So those are the options of how we can receive information about a function. So we're going to differentiate this function, right? How do you find the derivative when you're given the function in these sort of modes? So how do I find the derivative when it's a table or a graph? I approximate or I estimate. Right? I've got points. All I can really do with points is do a slope, an algebra slope. So if you have a table or a graph, you're going to see the word estimate or approximate for finding derivative values. It's all you really can do. If you are given an algebraic expression, notice the color coding here, right? If you have an f of x equals, then you can use your derivative rules and differentiate that and get in a real live instantaneous expression for the derivative. So it's just a little a way of navigating what direction you're going to. Either you're going in an algebraic direction where we're using derivative rules, or we're going in an approximation direction, which is where we're using our algebra. So that approximation, as I said a little earlier, it represents the algebraic slope. And if I'm differentiating, I can differentiate even a couple of different ways, right? I can use a calculator, I can use my Math 8 button, or I can differentiate by hand and use my rules. So we even have some options here when we do have a function as to how we get that instantaneous value. Okay, so let's look at this example. Notice we're given a table. So let me go back to that previous screen. We already know we're here, right? So we already know we're heading in this direction. Okay, so I notice that's the calculator. I notice I have some units here in Fahrenheit and minutes. And I notice I have a function W of t. Okay, so now we're going to read the entire question. It says the temperature of water in a tub at time t is modeled by a strictly increasing twice differentiable function where function w, where w of t is measured in degrees Fahrenheit and t is measured in minutes. It's telling you that we have Fahrenheit and minutes. So when we talk about derivatives, we're going to be talking about degrees Fahrenheit per minute. At time t equals 0, the temperature of the water is 55. Okay, so we start at 55 and we have a strictly increasing. So look at the table, we start at 55 and it's increasing. The water is heated for 30 minutes. So notice that we're heating the water beyond where our table ends. We begin at time t equals 0. Values of WT are at selected times for the first 20 minutes are given in the table above. Use the data in the table to estimate. So we know we see the word estimate. We know we're talking about algebra slope. Estimate W of 12. Show the computations that lead to your answer. In other words, they want to see a slope set up. Using the correct units, interpret the meaning of your answer. Okay, so we know it's a calculator. We know we're doing algebra slope because we see estimate. We know we have a starting amount. Temperature is 55. So they're wanting us to estimate W prime. So estimate dW dt, right? Or W prime. Okay, so W prime of 12 is approximately equal to, this is important because we're estimating, right? So at 12 minutes, that's right here between 9 and 15. So those are the points we should use. And College Board does this all the time with tables. They love horizontal tables, but the downfall of the horizontal table is that the minutes, the independent variable, is on top, and the dependent variable, the function values, are on the bottom. And we know that when we set up the slope expression, we need to put the function values on top. So these values need to go on top. So I take my 67.9 minus my 61.8, that's my rise, over my run, 15 minus 9, and there is my estimate. So it says use the data in the table, show the computations. Here's our computations that lead to your answer. Using correct units, interpret the meaning of your answer. So when it says use the correct units to interpret the meaning, it's basically saying, or really literally saying, just what are the units? So we can calculate this if we want to, but we can also leave the expression as this as an answer. So kind of keep that in mind. You don't have to do the calculation that gets you 1.017, but you can if you want to. And then it says, so it says using the correct units, interpret the meaning of your answer in the context of this problem. So it wants a statement here. Okay, so the temperature of the water is increasing at a rate of 1.017, and then now they need to see the units here. So we grab these units. We have Fahrenheit over minutes. That's exactly what we calculated here. Fahrenheit over minutes. So degrees Fahrenheit per minute. And so that would be this would be giving the meaning of the answer in terms of context, in terms of the context of the problem. At time t equals 12 minutes. So this was the approximation at 12 minutes. Okay, so let's take a look at example 2. Also a calculator problem. It says the tide moves from a sandy point beach at a rate modeled by function r, given by this expression, 2 plus 5 sine 4 pi t over 25. So we know we need to be in radian mode because we see a trig function. This is a pumping station adds sand to a beach at a rate modeled by function s. So that function is 15t divided by the quantity 1 plus 3t. So we literally add sand to the beach because the tide of the beach will wash the sand into the lake. Okay, so we have two things happening simultaneously. We have sand being added and we have the tide removing sand. So both R of T and S of T have units of cubic yards per hour. T is measured in hours for the first 6 hours, and we start at time T equals 0. The beach contains 2,500 cubic yards of sand at time T equals 0. Let's find the rate at which the total amount of sand at the beach is changing at time T equals 4. So how is the total changing? So the total is going to be what you add, take a minus what you remove. Okay, so the starting amount of 25 cubic yards isn't going to come into play here because it just wants to know how is it changing. So we want to take the added minus the removed. So here's the amount added, there's the amount removed, and we want to know the rate at which it's changing. So when we see the rate at which, that phrase, we know that we have to differentiate this. So we need y, I'm going to call the change y, and so y prime of 4 is going to be s of 4 minus r of 4. So notice I'm not differentiating here. It's s of 4 minus r of 4. Doesn't that seem weird? But think about what we have here. Okay, this r of t is the rate at which the sand is being removed. It's not the amount of sand, it's removing at that rate. So this is already a derivative. And this is the rate added. So this is already a derivative. So this is really a derivative minus a derivative. And that's going to give me my rate of change. So all I have to do is grab those values from my calculator. So if I plug in 15 times 4 divided by 1 plus 3 times 4, I'm going to get this. And then if I grab 2 plus 5 times sine of the quantity 4 pi times 4 divided by 25, I'm going to get that. And so we have an answer now that is negative 1.909. So the negative sign is really significant. Okay, it does not ask you to explain, so don't. It's just it's saying find the rate at which the total amount of sand is the beach is changing. This would have been an okay answer. 4.6154 minus 6.5241 is no acceptable answer. So it's not asking you to explain it. It's not asking you to give units, so don't. So here's the answer. It's just looking for a numeric answer. The negative sign, though, is telling you that more sand is being removed than is being added. So we're losing sand. So that's what that negative sign, if it would ask you to interpret what does the sign of the answer mean or something like that, that's what it would be. That's what it would indicate. If it would ask you for units, then we'd have cubic yards per hour. And it mentioned that up here, cubic yards per hour in the problem statement. Okay, but doesn't ask you to explain either of those, so don't. So we know, and I already discussed this, right? We know the amount of sand is decreasing. So we can say it's decreasing at 1.909, or we can just say it's negative 1.909. Either one implies decreasing. Okay, let's take a look at this multiple choice question. So no calculator, so you got to put your calculator away. So this is the number of gallons of water in a storage tank is modeled by W of T equals 25 minus T squared. So this is the amount of water, okay? And that level is being monitored for 5 hours, from 0 to 5 hours. At what rate in gallons, or minutes, excuse me, at what rate in gallons per minute is the amount of water in the tank changing when we get to the 3-minute mark? So it's asking for the rate of change at T equals 3. That's what that phrase is saying. And we don't have a rate, we have an amount. Okay, so we need to differentiate that. That's the volume of water. We need the rate. We need W prime of 3. So we need to differentiate the function. So differentiating that gets us minus 2t, right? 0 minus 2t. And when we plug in 3, we get a rate of negative 6. So the negative meaning that water is being removed from the tank at that rate. I don't think it mentioned, oh yeah, gallons per minute. So it didn't mention the units in the answer, but that's okay because they were just asking for the rate of change, which is a numeric answer. All right, let's take a look at example 4. So example 4 is a calculator question. So a 12,000 liter tank of water is filled to capacity at time t equals 0. Water begins to drain out of the tank at a rate modeled by R of t, measured in liters per hour, where R is given as this piecewise function. So it says find R prime of t when t equals 3. So coming back up here to this piecewise function, that means we're using the top piecewise function. Okay, and it says using the correct units explain the meaning of the value of the context in this problem. So we have to explain the context and with the correct units. So let's go back up here and look at the units. We've got liters and per hour. So we know the units are going to be liters per hour for R of t. So R of t is already a rate, and we're being asked to differentiate this. So kind of keep an eye on that as we go through the solution. Okay, we're going to grab our calculator. We're going to find the derivative at 3 of this function. So we're going to do a math 8. And then we have to explain it. So we're going to get to explain in just a second. So we need to do a math 8 on this function. Notice this, I mean, you can differentiate this using the quotient rule, but it's a calculator question, so please don't do this by hand. Okay, they give you funky questions when they let you use a calculator because they do not want you to calculate derivatives by hand. So use your math 8. Make sure your x plus 3 or your t plus 3 is in brackets, right? Because that whole thing has to be in the denominator. So make sure that happens. Divide bracket x plus 3 bracket and then evaluate it at 3, and you get 50 point stuff that you can ignore, right? 0.0000139. That's garbage. That's the approximation of your calculator working. So the answer here is 50. So we know that R prime of 3 is 50. And so you answered the question. Notice I answered the question using the notation that was given in the question. They want to see that. So make sure you say R prime of 3 equals 50 so that you have answered the question they asked you to answer. And then we got to find the correct units. We know R of t is in liters per hour. So if we differentiate R of t, we add another per to these units. So this is liters per hour per hour. So right here, R of 3 is positive, so the rate at which water is draining is increasing. So in other words, the rate at which the water is draining is going faster and faster and faster and faster. And at 3 hours, at 3 hours, that rate of draining is 50 liters per hour per hour. Notice the extra per hour because we differentiated a rate. Okay, so when we get into the classroom, we'll go over the takeaways from the notes and then work on the topic questions.